Okay, so in this video, I will consider a plane curve. So in the plane, I have my Cartesian basis, I have some random curve, I have a position vector to the curve, and the y-coordinate of the position vector is given as a function of x. So my position vector I can write as xex plus yey in Cartesians, and I can also write it as xex plus f of x ex ey in this special case. And for this problem, I want to determine et, en, and kappa as functions of x. So there are probably many ways to do this. Let us try maybe to start by saying that et is equal to the velocity over its magnitude, the magnitude of the velocity, which is the speed, v over the magnitude of v, which is the speed. So the velocity is just v is equal to the derivative of r with respect to time, dr by dt, equal to x dot, or dx by dt, dx by dt ex, plus df by dx, dx by dt ey. So here I use the chain rule. So that's dx by dt times ex plus df by dx times ey. That's my velocity, and my speed is gonna be the magnitude of v, which is dx by dt absolute value times the square root of 1 plus df by dx squared. Let's make an assumption that's gonna simplify calculations a little bit. Let us assume that I'm traveling on the curve such that in this way, such that dx by dt is positive. So I'm traveling in this manner. Assume dx by dt is positive, so I can remove the absolute value. V is equal to 1 plus df by dx squared times x dot. Okay, great. So going back here, I can write et as dx by dt ex plus df by dx ey over basically just the magnitude of that vector, x dot, which is again dx by dt, times the square root of 1 plus df by dx squared. These two terms cancel out, and I'm left with that. Et is equal to ex plus df by dx ey over the magnitude. Okay, that's awesome. We calculated et as a function of x. It involves the derivative of the function f, and it's been pretty easy so far. So for next, we want to calculate en. And en comes up in many situations. We can calculate en as coming up from a is equal to v dot et plus kappa v squared en. We also know that en, by definition, et is equal, or det by ds by definition is equal to kappa en, where en is a unit vector, or det by dt is equal to kappa v en. So maybe I'll take the derivative of et with respect to time. Let's see how complicated that is. It's because I know that det by dt should be equal to kappa en from here. Okay. Let us see. So det by dt, this is the time derivative of this. I'm gonna have to use the derivative of u over v. Basically, prime is u prime v minus v prime u over u squared. Okay, u prime, the derivative of the numerator, is d squared f by dx squared times dx by dt ey, that's u prime. V is the square root. 1 plus df by dx squared. And I think I can make my square root a little bit shorter. Awesome. Minus the derivative of the square root is going to involve derivative of radical u is u prime over 2 radical u. So my 2 radical u, starting with the easy parts, 1 plus df by dx squared, and then u prime is 2 df by dx, and then the derivative of df by dx with respect to time, that's again d squared f by dx squared dx by dt. Okay, over the square root squared, so 1 plus df by dx squared, and the square and the square root go away. Okay, so that's interesting. What I'm gonna do is I'm gonna just consider the numerator on its own for a bit, and I'll take a common factor for the numerator of 1 plus df by dx squared, all of it square root. The 2 and the 2 here cancel out, and I think both terms contain a dx by dt. So I'll take that outside, dx by dt. And then I'm left with d squared f dx squared ey times 1 plus df by dx squared minus df by dx d squared f by dx squared. I think there's something wrong. Yes, I forgot to multiply this term by u. So that would be multiplying this by ex plus df by dx ey. Okay, this is getting not complicated but long. We'll figure this out. df by dx squared f by dx squared ex plus df by dx ey. Okay, so that was just the numerator. So the whole thing, det by dt is equal to 1 plus df by dx squared to the power 3 over 2. Please do verify these calculations on your own. Times dx by dt. Yes, I do not think watching me do this is going to help a lot. Just going to give you an idea, but redo these calculations after you finish watching this video. And then times ex, I'll get... oh wait, I can take a common factor also of... I can take a common factor also of d squared f by dx squared. And then along ex, I'm left with minus df by dx ex. And along ey, I have 1 plus df by dx squared minus df by dx squared. Okay, cool. So that's a simplification in our long calculations. So det by dt is dx by dt d squared f by dx squared minus df by dx ex plus ey over 1 plus df by dx squared all to the power 3 over 2. Okay, let's remember our initial goal here. Our initial goal was to calculate en, and we have that dt by dt is kappa. That's equal to kappa v en. So all I know right now is that I can calculate En by considering a unit vector in the direction of in this direction, basically. A unit vector along this is gonna give me En. So a unit vector along this direction. En is gonna be equal to minus, or Ey, minus df by dx ex over the square root of 1 plus df by dx squared. And then I know that all the rest should be equal to kappa v. Kappa v should be equal to dx by dt d squared f by dx squared over 1 plus df by dx squared. That's kappa times v. And I already calculated v, the speed, over here. So maybe I'll just copy that. Copy. Paste. So I have these two, then kappa is equal to dx by dt d squared f by dx squared over 1 plus df by dx squared over x dot the square root of 1 plus df by dx squared. The x dot and the dx by dt, these are the same. I'm left with d squared f by dx squared over, I can put it just to the power 3 over 2. Okay, and if we did not do any mistakes, that's the equation for a plane curve. And here I assume that x dot is positive early on in my calculations. Okay, that's great. Thank you so much.